Hi, this is my presentation on electronic absorption spectroscopy of a series of homologous conjugated dye molecules. My name is Burton Carty. So, starting with our introduction, the main objective of what we're doing here is we're examining how the wavelengths of light absorbed by, like I mentioned, this homologous series of conjugated dyes change when that conjugated chain of pi bonds in these dyes increases in length. So we can see an example of one of these molecules down here. This is the 3,3-diethyl thiocyanine molecule, or we're calling dye number one, circled right here in the white circle. This is our conjugated chain. Um, Really what we're going to really see here is a delocalized series of pi orbitals, or the electrons in those pi orbitals. That's going to be what gives rise to the molecule's ability to absorb light and present in a particular color as a dye. So why does this matter? Why do we care? So understanding the energy that is required to promote electrons to an excited state has very many practical uses. If we're looking on the organic chemistry side of things, we could efficiently use light of particular wavelengths, very specific wavelengths, to excite the electrons that we find in this conjugated chain. And it's going to make those electrons more available to bond with other molecules. And that would make it very easy to do so. We can just use a specific wavelength of light, be very efficient with it. This also opens the door to the use of theoretical molecules to find a wavelength of light absorbed by molecules instead of using experimental methods. So instead of going through with every single molecule that we want to test, just predict it with a mathematical model. We don't have to waste the resources on experimenting with everything that we want to learn about. So moving on to the main research question here, which is, can theoretical models of molecular orbitals give us accurate values for an electron's transition energy to an excited state? So we're looking at both sides of the hypothesis. There's the null hypothesis here, where we're kind of thinking theoretical molecules, looking at the approximations that we're going to be using and the computational molecular models that we use in SciGRESS. They're not going to be accurate enough to act as a substitute for experimentally determining transition energies. Alternatively, what maybe we were hoping to see is that perhaps the SciGRESS molecular model calculations will provide accurate values for the transition energies of these dyes, and we might also expect them to be more accurate than the particle in a box and the Huckel approximations that we're about to talk about, just due to the fact that the particle in a box and the Huckel approximations, they make many assumptions, they ignore certain aspects for the sake of simplicity, right? So moving on to our theory here. So looking at the models that we're using, like I said, we're talking about particle in a box, the Huckel molecular orbital theory, and the neglect of diatomic differential overlap semi-empirical models. So the models more specific that are being used there, we're testing four methods. That's the MNDO method, which is kind of the basis for the other three methods being used. There's the AM1, the RM1, and the PM3 as well. And we're going to talk more about those in a little bit. So looking at the particle in a box model, it's kind of just treating any one electron by itself. So it's an electron in a conjugated system of p orbitals in the pi bonds. And we approximate to being inside a one-dimensional box of the length of the conjugated chain of the molecule. So we define the energy for this electron by the equation over here on the right. So this is E equals n squared times h squared over 8ml squared. Our n meaning our principal quantum number of the electron, which is going to change based on the length of that chain, how many atoms are involved in that chain. Planck's constant, the mass of the electron that we're examining, which is going to be constant across all electrons, and the length of the one-dimensional box. The absorption of energy is going to give an energy transition, so that is going to be equal to the difference in energy of what we call the HOMO and the LUMO states. That's the highest occupied molecular orbital and the lowest unoccupied molecular orbital. We're going to define those as n sub I and n sub I plus 1. Moving on, talking about the Huckel molecular orbital theory. This particular model makes a few approximations about it. It does kind of consider the orbitals on other atoms and a little bit of the electrons being used in there, but there are still quite a few approximations being made. So if we're looking at the matrix that we would set up using this, because it's a linear combination of atomic orbitals, meaning we're just kind of adding those orbital energies together, right? So looking up here on this top left box, we have the H sub 11 minus E sub S 11. So the H sub 11, this would be our electron energy for an electron in the orbital of energy level 1. And we're subtracting from that term, the same energy times its orbital overlap. The orbital overlap is going to be 1 here because the orbitals overlap with itself. It's completely overlapping. It's 100%. So we see that all the way down here, this S is going to end up simplifying to 1, which we see down here when we equate H sub 11 to alpha. Over here, right here, we see the H sub 12 minus ES12. This is the atomic orbital energy for 2 orbitals in adjacent atoms. And from that, we're subtracting energy times the S sub 12. S sub 12 for here in the Huckel approximation, we are making the assumption that it's 0. There is some bond overlap, orbital overlap, but it's considered minimal, so we're just equating it to 0. So this just simplifies to H sub 12, which is going to be what becomes our beta term down here. And basically make these assumptions throughout the whole matrix. So what's going to end up happening is that the diagonal turns into alpha minus E all the way down, and the adjacent diagonals are beta all the way down. Everything else in the matrix is going to end up being 0, so it ends up being a pretty simple matrix. We can kind of see what that looks like over here on the right. So this is using MathCAD to find some values here for the die number 1. So here what's happened here is we've used X to substitute in for the value of alpha minus E over beta. And we got alpha minus E over beta because we divided everything in the matrix by beta. So all our beta terms became 1, really simplifying the matrix. And we're just kind of plugging an X in for that alpha minus E over beta. So then we find the determinant of this function and we solve it. And we get the values of 0, 1, -1, the square root of 3, and this negative square root of 3 for our X values. These X values are going to end up being our coefficients for our beta term in this equation down over here, which gives us the energy levels of our electrons, or of our orbitals, I should say. Alpha is going to end up being 0. That's where we set the orbital energy to 0. And so, which is fine because we're mostly just interested in energy transitions, not actual energy values. It's more that energy transition value, which is going to be the same regardless of whatever alpha is, because the only thing that we're changing here is the X times beta term. And beta is constant as well. So the only thing that's ever changing is this coefficient of X, which we have the answers to over here. And that's going to give us the energy of each of our electron orbitals. Moving on, we're moving on to the NDDO. There can be 4 different NDDO computation methods that are going to be used in this experiment. So we have the MNDO method, which is based on the NDDO integral approximation. The M1 method, which compared to MNDO, reduces the repulsion of atoms at close separation distances. PM3, which considers parameter values optimizable, in contrast to AM1, which uses spectroscopic measurements for some of those parameters. It also uses 2 Gaussian functions always for the core repulsion function, as opposed to an AM1 where there can vary from 1 to 4 of these Gaussian functions. And then RM1 has the exact same number of parameters and the same types as AM1, but has taken the same approach as PM3 as having optimized the values instead of just using spectroscopic measurement. Now, the methods for doing this, we're going over the materials real quick. So we're using an Ocean Optics 4000 CCD spectrometer with a custom optics table, 2 biconvex lenses with a focal length of 150 millimeters, 2 turning mirrors, light sources, which is kind of a combination of standard incandescent light bulb and an ultraviolet LED to fill in for the areas of the UV visual spectrum that aren't covered by the incandescent light bulb. These are each powered by their own separate power source. We're using the Logger Pro software, and we're also using cuvettes to hold the dyes that we're using. So we're also using dyes 1 through 4, of course. So this is just kind of giving us a look at what our setup looks like. So on the top, actually bottom left, is where the light source is originating from. It is going to project about 300 millimeters to the first biconvex lens, which is going to focus the light onto this turning mirror, which is another 300 millimeters away, which is going to pass through the cuvette chamber or your dye sample, hit this other turning mirror, go through this other convex lens, and into our spectrometer. And then we're taking the absorption spectra of the light that's passing through the cuvette. So what wavelengths of light are getting absorbed and which are coming back through the other side. And move on to what the extra results we got for those experimental values. So here is our graph of the absorption spectra. Dye number 1 is red, 2 is orange, 3 is yellow, and 4 is green. The maximum wavelengths have been marked on those peaks. And we can see what those actual values are over here. So 423 nanometers for dye 1, 557.5 for dye 2, 650.7 for dye 3, and 742.4 for dye 4. And we see because of corresponding transition energies and electron volts, which what we're going to be using for our comparisons later on to our other methods that are more theoretical rather than these experimental values. So we're moving on to the particle in a box model. I'm going to talk a little bit about how we're defining that conjugated chain length. So we're just taking the length and obstrums of each bond, starting from nitrogen, going from nitrogen to nitrogen. So that's this bond plus this bond plus this bond plus this bond, plus 1 bond beyond each of these nitrogens. And the reason that we do that is because these p orbitals, where these pi bonds are forming, the electrons are delocalized. They don't just come to the nitrogens at the end and they stop right there. They kind of move past it a little bit. They delocalize a little further, and which is even supported by this additional benzene rings here on the cyanine moieties. So I've drawn a box around each of the conjugated chains for all of our dye molecules. So they're all kind of extending that way. Let me move on to the next slide. Here's our results for the particle in a box model. So main thing we see is the lengths that we're actually calculated. These are in meters, converted from angstroms. We see the change in energy in joules and then in electron volts. Also find the wavelength and maximum absorption for comparison, and we calculate the percent error. So I'll talk more about this later, the percent error in this compared to our experimental values. So now we have the results for our Huckel approximation. So over here on the right is how we found our beta value, right? We charted the beta coefficients that we calculated in MathCAD. And I have diagrams of the molecular orbital energies. The electron filling is a bit off. The air has kind of got moved around. But we can see the coefficient values starting from the lowest lowest energy level up to the highest energy level that we have for each of these molecules, each of these dyes. And then, so we took the difference between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, and I use that for these change in beta coefficients because that's what's going to be changing in our calculations. And we charted that, graphed that against the experimental change in energy in electron volts here. And from that, we got this equation here. This is the slope, the linear slope formula for it. And our beta value is going to be this slope right here, negative 2.6026. This was then used to calculate with the change in beta coefficients, our theoretical energy transitions for the Huckel approximation. And we can kind of see that there's kind of a decent amount of error here, and we'll talk more about that again later. And then moving on to all our NDDO models, I'm not going to spend too much time talking about each of these. Basically, we have the maximum wavelengths of absorption that we calculated for each method and the percent error over here. We also have the average percent error for the method to determine which method is the most accurate. Over here on the left, we see the actual graphs of the absorption spectrum. They are labeled 1, 2, 3, and 4 in sequential order. All the graphs follow the same format where the maximum absorption increases with each dye as it increases in length. So this is MNDO, AM1, RM1, which happens to be our most accurate, and PM3. And then here on our final results slide, we have a table kind of summarizing all our findings. So we have the experimental values that we found, the particle in a box values that we calculated, its percent errors, the Huckel values that we found and calculated and their errors, and then using the most accurate of the Sigris models, Sigris methods, the energy is calculated with that and their percent errors. Now, something that you're probably noticing here is that for our smaller molecules, dyes 1 and 2, generally speaking, these models aren't great predictors for the change in energy. R1 does a pretty decent job for dye 2, but not that great. And for particle in a box and Huckel, it's just not doing a good job at all. We still have a lot of error there. It's not getting a very accurate value. Now, when we come down to these larger molecules, these particle in a box in particular, and RM1, kind of are much more accurate at predicting those transition energies. And we might think of that because of the fact that we're making approximations, especially towards the ends of our conjugated chains. In our larger molecules, there's a lot more chain there, which is going to contribute to that transition energy. But in our smaller molecules, there's not a whole lot there. So a lot of that transition energy is also going to be important to consider from the ends of the molecules that we're not considering at all, right? A lot of that energy is coming from there and its ability to elevate the electrons. So moving on to the next slide, we're going to talk about was the hypothesis we made confirmed or rejected? And it kind of depends on the molecule, the method that we use, just like I was talking about. So those larger molecules generally had more accurate predictions from the models than the smaller molecules. Like I was saying, this applies particularly to particle in a box in the RM1 method. And the smaller molecules generally just had poor predictions from all the models. Huckel more accurately predicted energy transitions from smaller molecules than large molecules, within its own comparison, but still was not a very reliable method of doing this. Pause a second. I wanted to talk a little bit about why the Huckel method might not be all that accurate. So let's go back to the results for a second. So we can kind of see here that Huckel just generally was not a very accurate model. And there might be some pretty good reasons for that. Yes, it's making approximations about orbital overlap in terms of the adjacent molecules. Another thing to also consider is the fact that the Huckel approximation generally, and especially the way we set it up, is meant to account mainly for just the carbon chain. But the chains that we were looking at actually had nitrogens on the end of that. And when you're using the Huckel approximation, when you have nitrogens, we can't just equate the values for energy. It's just alpha. It becomes a little bit more complicated than that. Usually you're supposed to use actually a term called alpha minus H beta, and H it's not the Planck's constant, it is a particular value that is determined based on the type of atom that you're looking at. And that could be a source of major error, could be a source of error in these Huckel calculations. So if we modified our way of calculating it by the Huckel method, we might get more accurate results. Now, as far as particle in a box goes, kind of talked about earlier how it neglects electron-electron repulsion in its energy calculations, which is an important part to the energy of these orbitals, these electrons, right? If we're neglecting those terms, it's going to affect our accuracy and our ability to predict these models. All right. As far as final statements goes, I think that best bet for using a theoretical model to predict these transition energies is to use the ARM1 molecular model method. It just had the most accurate results, especially with those larger molecules. I think when you're dealing with the smaller molecules, that the method that we use to calculate these transition energies, you have to have a different approach or something. But ARM1 should work for any molecules that have much longer conjugated chains. Anything that's shorter, it might be better to just use determine those values experimentally. Thank you.